Hi, this is a post-recording of the 5th lecture in the summer Haskell class. It's a post-recording because when I gave it on Wednesday, I forgot to record it. So I'm going to go through the material again and make it available for posterity. I'll try to give a little extra time to the things that people had questions about the first time around. So without further ado, type classes are Haskell's airship quest. What do I mean by that? I mean that, in a typical console RPG, you go from boss to treasure in a very linear plot, grinding some levels out until you get the airship. And then when you get the airship, the world opens up. You can free the monads, or you can fight this green dragon in the corner, or you can go after the golden lambda. Whatever you want to do, the world opens up. And that's what type classes do for you. And the infamous monad is just the first really hard boss. It's actually not as hard as this boss in Final Fantasy IV, because if it were, that would be dreadful. And all it is a type class. Now we're going to focus on some of the simple type classes in this lecture, and then in Monday's lecture, number 6, we'll focus on the more complicated ones. So first, let's talk about equality. Every language has some notion of it, and often they get it egregiously wrong. But what does getting it right look like? We know that JavaScript and PHP are notorious for bad definitions of equality, but what does it look like to get it right? Well, math. We want the equality operator to have these 3 properties. It should be reflexive, which means that for all x, x equals x. Pretty common sense. One symmetry. If x equals y, then y should equal x and vice versa. And finally, we want transitivity. For all x, y, z, if x equals y and y equals z, then x should also equal z. And those are properties of what's known as an equivalence relation in mathematics. It divides a set into classes of things that are equivalent or, in some contexts, indistinguishable. In Haskell, checking for equality is a pure function. So based on the type signature, we know that it requires the A that we're comparing to itself to be an eq type, and it returns a bool, and there's no IO around it. So the value of x equal y, that's the operator that returns true if they're equal and false otherwise, should never change. Has to be stable. So value equality is a notion of equality in which x equals y when they contain the same value. And that concept can be type specific. For example, in the double type, which is floating point, 0 and -0 are equal because they correspond to the same mathematical value. They're different bit patterns, but they're equal in the real number system, so we have them equal in the double type. You could do a non-conventional value equality if you want your type to have different semantics. So here we have a type called intSet, which is a wrapper around a list of ints. But for our equality, we consider 2 intsets equal if they have the same members. Sort sorts them in ascending order, and nub takes the uniques. So what we're really saying is, if these 2 lists, which may be different, represent the same set of integers, remembering that a set is unordered, then they're equal. So in the first case, the fact that there's a duplicate 2 and the fact that there's a different order doesn't prevent them from being equal. Now, that's a case where the representations underneath are different, the lists that are used to realize these sets, but they both represent the same mathematical value. So as sets, they're equal. Object equality, on the other hand, is the strictest definition of equality, where x and y are only equal if they're the same thing. That is, the same object in memory or the same pointer. For immutable values, we want to prefer value equality as appropriate to the type. Doesn't matter which 3 you're holding on to, they're all the same number 3. And that will almost always have a straightforward definition. But for mutable objects, the only acceptable definition is the stability, or is object equality, because of the stability mandate. Even if 2 mutable objects have the same state now, they might not have it later. So we say that they're not equal because they can't be guaranteed to be equal at all times. That's different from what you're used to if you work in, say, Java, where 2 integers, the uppercase integer, the object, will be equal if they have the same value. So, as a question that I asked when I gave this class, what should this print? We have IORef, for those who haven't seen it, is a mutable reference cell that you can only access or create in an IO action. So new IORef takes a pure value, type A, and in an IO action, it creates an IORef with that A. Read IORef is an IO action that reads such a ref, and write IORef is the IO action that writes to an IORef. The question is, what do we expect this to print? And the answer is that the first comparison is false, because even though the IORefs have the same state, they're both 5s, they're not mutable. Or they are mutable. So they're not the same thing, so it's false. But then x equal x, well, that's obviously true, no matter what you're dealing with. So then what about cross-type equality? If a single type has an eq instance, we can use the equal and not equal operators that apply to that type. But how do we do cross-type equality? How do we handle the fact that we might want 0 in the int type to be equal to 0 in the double type? I'm going to pause for about 20 seconds and give the viewer time to think about it. The answer is that cross-type equality is a terrible idea, and it doesn't exist in Haskell. It does in Scala. It definitely exists in Java, but in Haskell, we just have abandoned the notion outright. It's not valuable. If you want to compare 2 things in different types, you should probably convert and get the equality semantics of the relevant type. And I'm going to show why it's such a bad idea. Let's pretend that we can define equality between an integer and a double, remembering that double is IEEE 754, double precision floating point. Now, the integer 10 to the 50 can't be represented exactly in floating point. There's a floating point number that's pretty close to it. That is usually written as 1E50, the literal. So we would say that that double and that integer are equal because that double is the closest floating point number to the integer whose value is exactly 10 to the 50. But 10 to the 50 plus 1 is going to be mapped to that same double. Almost certainly. I haven't checked it, but I'm going to assume with high probability that it's true. And we have a transitivity violation. You have integers that are different, and the integer type will acknowledge them as such, but they would map to the same double. So cross-type equality is bad. Okay, so why isn't the function type an eq type? Why can't you define equality on two functions in Haskell? The answer to that is because there is a valid definition of function equality. It's a real thing. It's a mathematical concept. We discuss it all the time in real analysis, functional analysis, but for arbitrary functions, it's computationally intractable to decide whether two functions are equal. If we have two double-to-double functions, we would have to do 2 to the 64 checks because they're close to 2 to the 64 double precision floating point numbers. And in fact, you can encode an arbitrary mathematical problem into integer arrow bool, where that function, let's call it m, is the question of whether an integer represents a proof of an arbitrary problem in Gödel encoding. And obviously, there's no way to solve arbitrary mathematical problems. So comparing such m's to the constant false function is formally undecidable. That may be a pedantic way of going about it, but the point is function equality does have a definition. It has a mathematically valid basis, but is computationally intractable in some cases. So now let's talk about defining equality for your own types, because with all these type classes, you will often want to make types that you create live in certain type classes. So then the question is, what is the right equality definition for tree? And the discussion when I gave this class came around to exactly what I hoped for, which is that it's going to be value equality because this is an immutable type. It's going to require the same contents and the same structure. So going a little deeper, you're saying that empty equals empty. Empty does not equal any node. And if you're comparing two nodes, first you compare the ints, and then you compare the subtrees. And that's a recursive definition by induction on the tree structure. And it looks like this. Now, let me show you what it looks like to create an instance of an existing type class. You will write instance, the name of the type class, the type, where, and then you'll define your methods. And most type classes, actually all of them, have some set of methods that you have to define. You will not necessarily have to define all of the methods that are supported. For example, with eq, you can define equality, that's the double equals, and it will derive not equal from it. It's relatively straightforward in that case. So instance eq int tree where, and we're defining the equality check method, and we have 3 patterns. Empty is equal to equal, nodes are equal if the contents, that is the int, and these int trees are equal, and otherwise we're comparing a node to an empty, and that's false. Okay, so then the question is, can this go wrong? It is a sound definition. It is the correct one, but it can go wrong if there are cycles in the trees. I believe that if you, and I should state that I don't know this for a fact, but I believe that if you make int tree strict in the subtrees, the other int trees, then you can't have cycles. But I would have to verify that to be sure. Okay, you can define equality badly if you want to. You can't break stability without subverting the type system. You'd have to be doing I/O in a non-I/O value, but you can break the other rules. So here's a borked int whose equality definition is complete garbage. It's not reflexive, it's not symmetric, and it's not transitive. Because we're calling n2 greater or equal to n1 if n2 is greater than n1, but no more than 10 greater than n1. If you break the contract for a type class, you can cause the compiler to make wrong optimizations. The compiler knows about eq, it knows about ord, it knows about monad, as we'll talk about when we get to do notation. And if you start breaking type class contracts, it's kind of like undefined behavior. Now, almost always the type class's contract will be really easy to fulfill, or it'll be really easy to know that you're fulfilling it. So yeah, don't break the contract, don't break the contract, and don't break the contract. Okay, does anyone, when I was giving the class, I asked if anyone had questions about this polymorphic tree definition. Instead of int tree, we have tree, which is empty, or node A, tree A, tree A. And the question is there anything wrong with this definition? And I'm going to give about 20 seconds to think about that. The answer is that there is something wrong with it because we don't know that A is an equality type. It won't compile. Because x1 equal to x2 may not be a valid operation. So what we want to do is put a constraint on the instance. Say that when A is an equality type, tree A is also an equality type. And now we're good because we know that x1 equal to x2 is a valid thing to be asking about. You can think of these constraints on type class instances in two different ways. One is just to say, hey, tree A is going to be an equality type in that defined way whenever A is an equality type. When A is not an equality type, trees are still valid data structures. They just don't have well-defined equality semantics. Another way to do it, to think of it, which I have up top, is that we're saying that if you have a proof that A is eq, which is what an instance really is, it's a proof or it's a witness to a fact, then we can generate a proof that tree A is also eq. Now, many of these built-in type classes, eq, ord, show, read, have obvious implementations for the types that you're going to define. So down here, I'm defining my type is constructor empty, my type, takes an int, a list of ints, and a string, and I say deriving eq and show. You can do that in GHC or in GHCI, and that will automatically derive them in a sensible way that will usually match your intuition. Usually that's what you want to do. You don't want to define your own type classes unless you have performance needs or you need different semantics from what the compiler is going to derive for you. And I'm going to go over how exactly it works. For eq on an immutable data type, it's going to be structural equality. If all the fields are the same, they're equal. If there's any difference, then no. Eq has another member, not equal, and you don't have to define it. It's got a default definition. And you could alternatively define not equal, and it would auto-derive equality. So then the question is, why might you define both? It's for performance. It's pretty rare, but you might have a case where you want to check for equality in one way when you think x is equal to y, and another way when you think they're not. Very low-level, detailed sort of case, but sometimes that comes up. But in general, you should just let the compiler do the derivations because you know the compiler is going to be right. For example, there's a contract, which is that equal, equal, and not equal will always be negatives of each other. if you define your own definitions, it's your responsibility to make sure that that's still true. Next, we have ord, which is the comparison class. Things that we can compare. It has an equality or an a constraint. So to be an ord type class, it has to be eq. It can't not be. But it has additional members. It has compare, which takes an a and returns an ordering, where ordering is this three constructor type, LT, EQ, or GT. And then it's got your greater than, less than, greater than, equal, less than or equal operators, and min and max. But you only have to define compare and it will figure out all the others. So here's an example where we have levels in some system, beginner level and advanced level, and we're defining the comparison so that beginner is always less than advanced. Makes sense, right? And if we have two levels of the same kind, beginner against beginner or advanced against advanced, then we compare the numbers. So as you see on the right, beginner 5 is less than advanced 1, max of advanced 10 and advanced 3 is advanced 10, and the sort, well, that does exactly what you'd expect. It sorts the beginner levels, then the advanced levels. So here's an ord example on list. The empty list equals itself. The empty list is less than any non-empty list, and vice versa, any non-empty list is greater than the empty list. And if you have two non-empty lists, then first you compare the heads, and if they're equal, then you compare the tails using, this is a recursive definition, you're defining list equality in terms of another call to the same thing on smaller lists. But assuming these lists are finite, that will always terminate, and that's your alphabetical or lexicographic comparison. What if you want a different ordering? For example, you may want the Java style string comparison, where it compares on length first. Presumably that's going to be faster if you just need an arbitrary sort because you're less likely to have collisions on length. That would actually not work in Haskell because list length on a linked list is O(n), but never mind that. Let's just say we want a different ordering. Well, you use new type, which creates a brand new type out of an old one with exactly one single field or unary constructor. So it's purely a wrapper type. In this case, we're calling it QList. It's exactly isomorphic to a list. It's just a wrapper, but it has a different equality definition. It compares the lengths first, and then otherwise it will default to lexicographic comparison, which is what Haskell ships with. What's the difference between a data and a new type declaration? That's a common question. The answer is that the regular data constructor version will keep a constructor tag and say, this is a wrapped int D. With new type, the tag is just thrown away. So at runtime, the wrapped int n is just an int. So the types are only distinguished at the compiler level. You get all the type safety, but you don't have the performance overhead because at runtime, it's just an int. Ord has a contract, just like eq. Two things compare EQ if and only if they're equal. So that's a contract between ord and eq. Compare AB is the negative of compare BA. So if one is LT, the other is GT. And finally, we have transitivity. So if A is less than B and B is less than C, then A is also going to be less than C. The derived ord instance is worth knowing. When you use deriving ord, which you often will, if you have two constructors, or if you are comparing values in different constructors, the left more constructor's value is always smaller. So, for example, with let's create our new with this maybe type, it's going to behave exactly like the regular maybe type. But if we did it this way, then the nothing in that maybe type is the maximal value. And furthermore, if they're in the same constructor, then it's lexicographic, like with list comparison. It'll do the first field. If those are equal values, it'll do the second field, and so on down the line. And if they're all equal, then they compare equal. So show is the toString class, not very interesting. Usually you'll derive it, but if you want to implement show, sometimes that's useful and you can do it. Read is the fromString class. I would say it's generally not worth it to write your own read methods. It's a little more complicated than just writing read. I think there's reads prec, which handles precedence. And at that point, you're better out just using a real parsing library like parsec or add a parsec. We're going to work with parsec in the second lab, so you'll see how that works. And again, you should usually prefer Safe's readMay function over read. So what if you want to create your own type classes? So for example, here we have a hashable type class. I'm just going to call it hash. There actually is one, but for now, let's pretend not. It has one member, takes an A and returns an int. So the instance for int is obvious. Just use id. For char, we'll use ord from data.char that converts a character into its code point. For bool, if it's true, 1. If it's false, 0. Nothing very interesting here. For tuples, we will hash the first element and add it to 37 times the second element. And for a list, we will first take the constructor tag as a number. So if it's empty, that's 0. And if it's a consel, then that's 1, plus 37 times the first element, plus 37 squared times the hash of the remainder of the list, which itself could be a recursive call. This may not be the most performant thing, but it would work. We recall creating a type called event, which had 3 constructors: error, corresponding to some kind of error in the browser; key char, which corresponds to a key press event; and then click, which comes with 2 integers. And likewise, we can define our hash for that event. Now, if you're creating an instance of a type class that already exists for a new data type, then that instance will live with the new data type, because you probably don't want to be changing the code of an existing type class or that existing module. And if you're creating a new type class and putting existing data types into it, for example, when I said I want int to be hashable, then the instance is going to live with the type class. So the instance will live with the data type if that's something you created, with the type class if you created the type class and want to put an existing type into it. But what if you don't control the type or the instance? Well, it's legal to define an orphan instance in another module, but it's usually a bad idea. This is a problem that Scala is facing with implicits, and it's a nightmare. Because if you have a class C, type class that is, and a type T, they have two different orphan instances, then you can have methods that mean different things in different parts of your code base. So what you should do instead is wrap a new type around the target type. You're saying, okay, this is my new type around the existing type. And it's a different type. It has different behavior. And you're not going to have the implicit hell that you can get from orphan instances. Now, Monoid is probably the first interesting type class we're going to talk about. It's got an empty. So any monoid A has at least one element that's called empty. It's kind of an identity. We have mappend or mappend, which takes two A's and combines them into another A. And then there's mconcat, which you don't really need to define because that's just going to take a list of A's and mappend them together. Now, I'm often going to use E as shorthand for mempty and a diamond, or two angle brackets together, as shorthand for mappend. And we have these monoid laws. So the empty, if you mappend it to an X on either side, you don't change it. The other law is associativity. So if you have F mappend, G mappend H, it doesn't matter which order you do them in. So list is an obvious monoid and has an intuitive definition. The empty list is mempty and mappend is append. Nothing surprising there. If A is a monoid, you can make maybe A a monoid. Mappend is nothing. Because nothing is the identity, appending nothing to something is going to leave it unchanged. And if you mappend two justs, then you mappend their contents, like you see at the bottom. Ordering is a monoid. Eq is the identity or the mempty. And if you compare to non-identity things, that is LT or GT, it favors the first. So what that's capturing is the lexicographic ordering, where you have different comparators that you could be applying to two objects, and the mappend of the results of those comparators is the lexicographic comparison of whatever you're comparing. Sorry if that was a bag of words. A tuple of monoids is also a monoid. Mempty is a pair of mempties, and that's not a circular definition because we're really saying that the mempty of the pair type is equal to the empty element of the A paired with the empty element of the B. And the mappend is just mappending on both the left and the right side of the pair. What about numeric types? So a lot of people look at this and say, well, yeah, integer should be a monoid because mempty is 0, or 0 is an mempty, and mappend is just plus. And that's valid. That is a monoid. But it's not the only natural monoid. You also have an alternative, which is where mempty is 1 and append is times. And since they're both valid, this is another case where you use new types to differentiate. So you have the sum monoid. It's a new type wrapper around a numeric type, and the monoid behavior is addition. And you have a product type where the monoid behavior is multiplication. A numeric type itself, like int, does not have a monoid instance. You have to decide which monoid you want, sum or product, by putting it into a new type. For bool, we have a similar situation where there are two valid monoids. So we have any, which is a monoid wraparound bool, where empty is false and m appending is disjunctive. It's ORing things together. And we have all, where the m empty is true, because the empty product of the empty and is true, or the and of an empty list of things is true by definition. Call that vacuous truth. And the m append is and. We have maybe refinements, first and last. That's different from the previous maybe monoid that I showed. With first, m empty is nothing. And if you m append two justs, you always favor the first one. So when you m append a bunch of firsts, you're going to get the first just. And when you m append a bunch of lasts, you're going to get the last just. My favorite monoid would probably be endo, which is a wraparound functions from A to A. And then the question, and I'm going to give about 20 seconds to think about this, is what is a good definition of m empty, and what would m append be? The answer is that m empty is the identity function. Takes x, returns x. And the m append of G and F is the dot, or the composition operator, which is associative. So what the hell is monoid exactly? It's associative, it's not necessarily commutative. It's got an identity element, and it's got a diamond append operation. But what exactly does it capture? Looking at these instances, it may not be clear. The answer, I would say, is that it captures reduction, as in map reduce. Or in Haskell, we don't use the word reduce, we use the word fold. So it'd say monoid is about folding. Some people have argued that monoid should be given the more accessible name appendable. But the problem is that, if you look at sum and product and last and first and many of these other monoids where you're deliberately throwing information away, you're not really appending. So it's more of the foldy class or the reducey class. It's things that you can combine together in a reduction. And this is where we get back to fold and fold map. Most Haskellers would argue that fold map is the canonical definition of fold. You have a collection of A's, and you have a function that maps A's into some monoid, and fold map is just going to map all those A's to the monoid, and then it's going to m-concat them. And fold itself just does the last stage of that, where it's got a list of elements in some monoid, and it concatenates them. Okay, so for an exercise, if you can, show how you would implement fold L and fold R in terms of fold map. And based on that, you might get some insight into why this first expression, where we're fold mapping over the any monoid on an infinite list, one dot dot, we're fold mapping those into the any monoid. That returns immediately, finds a true value, and it's done. And yet this fold L expression that we have, which should be equivalent in terms of what it computes, never returns. And the question is, why is that? And we are done. I will see you soon. Bye.